Hello there. In this video I'm going to be doing another review. This time it's on the Gochifix LG302, which is a low-cost 6,000 count multimeter and single channel oscilloscope. And I'd just like to give a big thank you to Banggood for sending this over to me for review. Actually, they reached out to me to do a review on this, and initially I was reluctant because there seemed to be a lot of low-cost scope meters on the market similar to this. However, the thing that caught my eye on this one is it is a 10 megahertz bandwidth scope meter, which shares the same Cat2 protected inputs with the multimeter and scope. And I thought, well, that's interesting because it make it really convenient for testing. Imagine you don't have to have another set of oscilloscope probes in addition to your meter probes. So I agreed, and as long as I could do a unrestricted and open review, which thankfully Banggood agreed to. Now, as this review is a little bit longer than I wanted it to be, I put in the contents here for you so you can use it as a reference and pop in and pop out as your heart desires. I'm going to start off with a teardown to understand how this thing's put together under the hood. And then I'm going to go down a little bit of a rabbit hole looking at the sampling rate for the oscilloscope. Actually, it's interesting. There's more to it than you might think. And then I'm going to look at the device architecture, summarize that. And then we're going to dig down on the multimeter and having a quick look at the measurement accuracy and its function. And then we're going to look at the oscilloscope and do a little bit of a bandwidth test. And we're going to look at an undocumented feature. I know this is a simple thing, but I think it's important because if you own one of these, you're going to want to know how to do it. Is how to turn off the audio beep. And then we're going to have a look at how it is to actually use. We're going to use it on a few real world examples. And then finally, a little summary. And now I'd like to take a moment to give a big thank you to the sponsor of today's video, PCBWay. PCBWay are my favourite PCB manufacturer and prototyping service. They have a really easy to use interface and can provide you with a quotation for your PCBs in minutes. And always look out for the offers. They always seem to have an offer on. And in addition to PCB manufacturing and prototyping, they also have a great makers community as well, where you can share designs with other makers. They also have a great makers store as well. You can get everything from test equipment to soldering irons. So PCBWay is a great one-stop solution for PCBs, PCB assembly, CNC, 3D printing and more. For more information, have a look at the link in the description. Okay, it comes in a very compact box. See what features it says it's got. So obviously multimeter waveform, that's an oscilloscope. It's got a screen, that's a good feature to have. Auto range, the usual resistance, current, resistance, capacitance, etc. Okay, continuity, frequency, all as expected. And you can see here it's obviously a 6,000 count meter. Basic parameters. We'll have a look at the key specifications a bit later. Oh, it's got a pouch for the meter. I always like a pouch. And standard issue zinc batteries. Okay. So first point there, it's not going to be rechargeable, which is not necessarily bad. If you're out in the field, you want to get to the shop to just buy replacements. These probes, standard issue probes. I think they all come out the same factory somewhere in Shenzhen or somewhere. They're quite sharp. Yeah, they look okay. Let's just get a magnet to see if I can feel any attraction between the cable and the magnet. No, I can't, so that's good. At least they're not steel. I have come across steel wires before in multimeter probes, believe it or not. They're a bit stiff, to be honest. Not very flexible, but they're okay. They get the job done. So we've got a quick start manual. Okay, let's have a look at the key points in the manual, in the specification. So 1000 volts DC, AC in 10 seconds. Cat 2 protected. 50 megasamples per second high speed sampling and 10 megahertz bandwidth with 6000 count meter. Waveform amplitude up to 1600 volts peak to peak. Current up to 10 amps. Auto sleep. Okay, so you can disable the auto sleep by holding F1 when you turn power on. Other key things I noticed. Now this might be a bit of a no-no for some people. Minimum voltage range on the scope is 500 millivolts division, but it goes up to 200 volts per division, which is quite handy. What else is notable in here? I did have a look through this. The peak hold is a useful function. We'll have a look at that later. Does minimum and maximum peak hold. It's really quite good. The relative function is another cool feature which can be used on more than just resistance. So we'll have a look at that later. Of course, you've got frequency and duty as well. And then the multimeter function actually has quite low current consumption for a scope meter, only 75 milliamps according to this, and only 150 milliamps for in scope mode. Maximum equivalent sampling rate, whatever equivalent means, 50 megasamples, input resistance 5 mega ohms, rather than the normal 10 for an oscilloscope. Vertical range, yeah, that's a problem, only down to 500 millivolts on the scope. It's a bit of an issue, and time base only down to 200 nanoseconds. So for a 10 megahertz scope, I would expect the time base to go down lower than that actually. But as for the multimeter, the specifications look quite reasonable because it's 6000 count meter, and the tolerances there look in line with what you'd expect at this price point. Notice it's also got capacitance and resistance up to 60 mega ohms, frequency up to 20 megahertz, which is quite high. Note that the manual warns you that if the battery goes low to the point where the battery icon is red, your scope meter readings might be inaccurate. Okay, let's have a look. Oh, so it also comes in a bag within a bag. I guess that's to keep it fresh. It's actually quite small. That's convenient for traveling or on-site work, I guess. It feels quite solid. There's a kickstand at the back. Obviously no other connections on it because it's not rechargeable. Well, it's quite firm. I'm not going to knock that out of position easily. And so the bottom there you see you got a shared oscilloscope and meter inputs, which I quite like actually. I can imagine it's useful. Okay, the battery insertion instructions on the back. So you have to insert the two outer ones first before inserting the inner one. Oh, that's because there's overlap. Let's get some batteries in there. So I'm going to use rechargeable 2400 milliamp hour. I want to try using the rechargeable because when I do my tests, I'll be using 1.2 volt batteries instead of 1.5, so it'll be a better test. Yeah, because you don't put the outside ones in first, you'll never get them in because they're partially obscured by the case. Okay. And here we go, system turn on. Let's see if you can get a better look at that screen. Okay, so it's quite clear. So go straight into scope mode. And then voltage. And you see you've got relative, peak, hold and select, and then ohms, capacitance, frequency and duty, current low range, current high range, and off. Okay, so there we have it. It's quite neatly laid out. Okay, the 4mm sockets don't look great, but that's what you'd expect at this price point. They have to reduce costs somewhere. Oh, and I see soldered in fuses. Again, another cost cutting measure, I would assume. I wonder if they're resettable or not. I guess we'll find out later. Some more unpopulated areas there for protection components. Maybe we'll find other protection components. It's a bit worrying this has got PTC and it's not there. Oh, I see PTC there at the bottom. It looks like we've got a couple of transistors, probably in a bipolar Zener configuration with surge transient suppression. There's a PTC, okay. And some series input resistors, probably where the input resistance comes from. Some MELF resistors there. So not too much going on in terms of input circuitry or protection, but then again, this is a Cat2 rated device, and also built to cost, so I wouldn't expect too much in the way of input protection. I see another, looks like suppression device missing there, or not populated in this model. If you look at the teardown I did of the Finersi 2C23T, I did a section there on discussion on what input protection could be expected in a multimeter and why it's there. So here is the optocouplers, and this here is the A to D, which is the MS9280, which is the same device as used on the Finersi 2C23T that I reviewed earlier. And then we have the connections between the microprocessor here and the display. Now this is a STM32F400, which is a 32-bit RISC microcontroller with 8 MHz clock, and there's the configuration EEPROM, or storage EEPROM. And what else we have? We have the buzzer, and then it's like we've got some connections for programming or debug and calibration. So they probably use it at the factory to calibrate the device, set the device up. And then we have the digital multimeter IC. It's there, driven by a 4 MHz clock. And then we have the multimeter configuration and calibration storage EEPROM here. Notice we've got an RX and TX connection here. Maybe that's the RX and TX connection between the multimeter chip and the microprocessor. What else have we got? Anything else to write home about here? Some more protection components under the end of the battery connection there. Notice a lot of traces going underneath that battery connector. I'm going to pull that battery connector off to see if there's anything under there. Oh, no, that was disappointing. Doesn't look like there's anything under there. So let's take the board out and see what's on the other side. Oh wow, looks like that's your lot. Obviously the connections for the rotary selector switch and the connections for the push buttons, and then you can see we've got our high current range shunt just there. No real voltage gaps I can see, spark gaps I should say. Very simple construction, obviously built to a cost. Anything under that display? No. So that looks like it's your lot. Looking at the construction of the case, again, it's built to a low cost, right? You pay your money and you get what you get. But this is pretty standard for this price range. And then I want to bring your attention to something. Look at the basic configuration of this multimeter chip. You see you've got the crystal, the 4 MHz crystal connected to the pin 1 row on the multimeter chip on the left there. And at the top you can see connections to a bank of capacitors, and then to the right bank of resistors. And then we got some data connections on the bottom left. Just keep those connections and configuration in mind for the moment, because I compared this to my UT61D, which is a very well respected multimeter with renowned accuracy for its price. Now have a look at this. Now this should look familiar, right? So again, we've got this IC with the clock crystal connected to the row 1 side, a bank of capacitors at the top, resistors and capacitors on the right hand side, and then bottom left some connection, some data connection to, in this case, the configuration EEPROM I should say. So it looks like it's using, and the crystal is just about the same as well. Instead of 4 MHz, it's got 3.999. So this is interesting. So it's got the same pedigree of multimeter chip as used in the well-respected UT61D. So that's a good thing. I now want to check the sampling frequency of the analog to digital converter. Now I know it's quoted at 50. But I did see the words effective sampling rate in the manual, so I just want to check it out. So I pulled up the data sheet for the MS9280 analog to digital converter. It's 10 bits, but I doubt very much it's using the 10 bits. It's probably using 8 bits, I imagine. And it does have a sampling rate up to 35 megabits per second. So there's the first question, right? So according to the data sheet, it capped sample at 50 unless it's being overclocked. But we can tell. Let's have a look. If you look at pin 15, that's the clock pin. So I'm going to put a scope on it and put it to oscilloscope mode and take a look. So I've got the scope connected to a test clip connected to pin 15 of the A to D. Then I'm going to switch the scope on, and I'm going to switch it on so it's set to 10 milliseconds per division. And I can see immediately that it's not clocking the A to D constantly. It looks like it's pulsing it. So it's reading on occasion rather than constantly. Let's try and work out what the clock frequency is, or the sampling frequency. So you can see it's 24 megahertz, 24.95. So it's 25 megasamples per second, not 50. Okay, that's the first thing. Next question is how often is it sampling? Just bear with me while I set this up. So it looks like the duty period's like 50-50 or more or less. Just set up the cursors so we can find out how often it's sampling. Okay, so it's about 1.89. So it's sampling is just less than 2 hertz, so it's sampling about just over twice a second. You can see that's 10 milliseconds. I change that to 10 seconds now, so it's the slowest scan speed, or the longest time base. Let's see what's happening now. That's interesting because it's sampling constantly when I've got the longest time base, 10 seconds per division. I'm going to change it now to the minimum, which is 200 nanoseconds. What is going on here? It's very faint, so that looks like a very occasional sample. So I've looked at it a bit closer, and you can see that there's a tiny period of sampling, a long period of nothing in between. So you can see here that the frequency's around 3.4 hertz. And then when it samples, you get 1.5 milliseconds of lower amplitude clock, which I measure to be 12.5 megasamples per second, and then 248 microseconds burst of 25 megasamples per second. So if I was to hazard a guess what it's doing, it might be in the 1.5 millisecond at 12 megasamples per second period, be looking for a trigger point, and then if it doesn't find a trigger point after 1.5 milliseconds, it just does a capture anyway at 25 megasamples a second to display on the next trace, and then that cycle completes. But that's just a guess. I mean, if you've got any ideas about what you think it's doing, then would love to hear your comments. So now we can piece together what makes up this oscilloscope multimeter. So you have an input circuit which shares everything with the oscilloscope input and multimeter input except for current. And so that will feed into both the ADC, which is the MS9280, being clocked at 25 mega samples per second. And it also feeds into the multimeter IC, which is like a dedicated MPU for multimeter functions. Now this looks like it's a DM1109EN from the characteristics of its pinout and performance. So what this actually is, it's actually a 9000 count multimeter IC, but the configuration EEPROM, which you can see underneath it, has been configured so that it's operating in 6000 count mode. So that configuration, along with its calibration information, is stored in the 24C02, which is the 256 byte I2C EEPROM. And then both the ADC and the multimeter IC feed into the central processor unit, the STM F400 series, and that's being clocked to 8 megahertz. And it attaches to a 32 kilobyte I2C EEPROM. I expect that's being used to store waveforms and maybe some configuration information as well. And then that drives our 240 by 320 pixel LCD. I've left out the other items for clarity, but basically that's what we've got. And now to check the current consumption. So I've got the original battery pack with a flute multimeter to confirm the input voltage, and then the Uni-T in series with the original battery connection on the PCB to measure the current consumption. So if you, I'm just going to put it in oscilloscope mode. If you remember my review of the Finersi 2C23T oscilloscope meter, the current was in excess of 400 milliamps, whereas this is just over 100, so that's excellent. And also with the Finersi, if I put it into multimeter mode, it still consumed over 400 milliamps. Let's do the same with this meter, and it only consumes around 55, so that's excellent. So now let's have a look at the basic operation of the multimeter. So I'm going to just go to the first selection, which is voltage. So you can see here I've got the basic menu options: relative, peak, hold, select and range. So press peak hold, and you see I start a run session, and it will record the maximum and minimum whilst that run session is running. And I can either stop that run session, reset it, or exit. And then I've got relative, which is very handy because it operates in many ranges, voltage, current and capacitance. And then I can select the sub range where it's AC. Interestingly, I can select frequency and duty cycle, even though it doesn't indicate it on the markings on the rotary dial, which is weird, but not an issue. And then we go to the next selection, which allows us to cycle around between resistance, continuity check and diode check. So use the select button to select the sub function. Again, you see you got peak, hold and relative, and range in the case of resistance. And then we go on to capacitance, and you see you've got the relative function available, again handy. And then you've got frequency and duty cycle, and use selection to select between the two. And then you've got low current range, where you've got relative, peak, hold and range all available to you, and select will change between AC and DC. And then finally, the same for high current. Of course, you've got to use the appropriate input connections on the bottom of the meter. And there you have it. very easy to use. I'm now going to start to measure the accuracy of the multimeter. So first of all, for voltage checks, I've got a voltage source. In parallel with the output, I've got a calibrated fluke, and then that feeds into a precision attenuator. And then the output, I've got going to 2 meters in parallel. So the UT UT61D, and of course the Gochifix. So first of all, I'm going to check 2.5 volt range. So looks good. The Gochifix almost identical with the unit T. And 5 volts, also good. Almost spot on. And 7.5, also excellent. And 10 volts, also good. Okay, so I'm happy with that. Okay, now we're going to take 1/5 of the input, should be 2 volts. And then 1/10, 1 volt, excellent. And finally 1/100th, should be 0.1 volt. 100 millivolts, so looks good also. Then I'm going to drop the range down, so I should get 25 millivolts, or 2.5 volts input divided by 100. So 25 millivolts, almost spot on. That's excellent. It's very good. Excellent. So now I'm going to check the DC volts input sensitivity. So I'm going to use this potentiometer and slowly raise up the voltage until it starts registering. So I've got a multi-turn potentiometer. I'm going to slowly bring it up. Okay, that looks respectable. You can see that I've got a millivolt range showing down to tenths of a millivolt on the unity, and you can see that the Gochifix seems to faithfully report the same range, even though it only goes down to tenths of a millivolt or hundreds of a microvolt. But that's okay. Okay, on to AC volt measurement. I'm going to start off with the low voltage range and millivolts. So I've got 5 volts on the input. I don't have a precision AC voltage source, so I'm just going to set 5 volts on the calibrated meter and just check how the other two correlate. So they're both a bit down, but interestingly to a similar amount. Maybe it's because they're using the same multimeter IC as we discovered earlier. And then that should be 1 volt, they're a little bit down also. But still acceptable, within 1%. And that should be 500 millivolts, also a little bit down. It's interesting that they're both using the same multimeter IC and showing a similar difference from the fluke. It should be 50 millivolts. Okay, that's kind of acceptable. You expect a lower tolerance on AC. But they're very close actually. You notice how close the Gochifix and the Unity are. That's interesting. Now let's check on the sensitivity using the same approach. I'm slowly going to bring up the voltage. Now it's interesting, Unity is already up to 0.5 millivolt and Gochifix is not showing anything. So we might have, looks like we've got a bit of an issue on 80 millivolt sensitivity on the Gochifix. Okay, now it's sprung to life. Maybe the 2 meters will agree at a higher millivolt range. Let's try turning it up. You see the Gochifix is a few millivolts down from the Unity. We know the difference is becoming less as we get towards 10 millivolts. So below 10 millivolts, looks like we might have a problem in accuracy. But above 10 millivolts, it seems to be in agreement with the Unity. And in case you're wondering, I did check the accuracy of the Unity before, and it was very good, even in the millivolt range. That's interesting. So now we're going to test AC high voltage. I've got all 3 meters in parallel because I don't have a precision AC source. I'm just going to check for agreement. So you can see 242 on all meters, so that'd be RMS. And now I'm just going to go into scope mode. And you see how easily I can do that without changing probes? That's one of the things I like about this meter. And I'm going to check what the oscilloscope says for RMS. I don't know if you can see that there, that's about 235. So I wonder why that is. That's quite significantly down from what the meters are saying, and indeed what the Gochifix says in digital multimeter mode. So there's a bit of discrepancy there. You just zoom in a bit. 234 volts RMS. Okay, so maybe the oscilloscope function for measuring RMS on the scope is not so accurate. Okay, so I'll put it back into multimeter mode. So change to AC. Okay, and then back to 242 volts. Well, at least the multimeters or at least the Gochifix multimeter mode agrees with the others. So looks like the multimeter section is accurate. That's good. I'm now going to measure the accuracy and sensitivity of the AC milliamp range. So I've got all meters in parallel, and I've got a AC voltage input from signal generator at 1 milliamp. And so first of all, 1 milliamp, you can see that more or less in agreement. And I'm going to reduce it on the signal generator. First of all, down to 0, and then I'm going to slowly bring it up. Okay, so I'll start to bring it up. Okay, and you see both meters are starting to register at 30 microamps, but it's quite different from the Fluke. See, the Fluke's got 46, and both the Unity and Gochifix are not registering. I bring it up to 50, 60, and they started to register, but they're quite out as a percentage. They seem quite insensitive on microamps AC. Okay, now things are looking better. Okay, so below like 60 microamps is not accurate, but then when you look at the resolution of the meter, it can only go into tens of microamps anyway. It's not too much of a surprise. But certainly by the time you get above 100 microamps, they seem to be in agreement. So I've got 50 microamps on the fluke. Yeah, only what, within 2%, 3% perhaps. That's okay, I think, especially at that current range. Now we're looking at DC amps. So I've got 1 amp, and obviously they're all in parallel again. And change that to 5 amps. Okay, that's good. I'm going to take it up to 6. Still acceptable. Okay, now I'm going to look at DC milliamps and sensitivity. So again, they're all in parallel. I've got 1 milliamp. So now I'm going to reduce it and slowly bring it up and compare sensitivity. So 80 microamps. $100 microamps, more or less. Gochifix is a bit out. Let me take it down even more to see where it starts registering. Yeah, I mean at the bottom end of the scale is way out. I have to remember that multimeters, in terms of the tolerance, are often specified in plus or minus digits. So when you get down to the last digits, you can expect them to be considerably out. So now I'm going to test the frequency function. So I've got 10 kilohertz. That's okay. Let's get to 100 kilohertz. That's all good. Then up to 1 megahertz. The fluke has dropped out. Let's bring it up towards 10 megahertz. It's 11, 13, and the unity's dropped out. It's supposed to be up to 20 megahertz on the Gochifix, so around 20, it's good. 21, 23, is it even going past that? 23, 24, 25, 26, 27. Okay, and we're out. Oh, so that's good. So comfortably measure up to 20 megahertz. It looks like with some headroom. Now we're looking at duty cycle. So we've got 50%. And 70, 75. bit below, but at least they're in agreement. It's 90. I mean, what you're using this for most likely is to test pulse width modulation for motors and such like, and I'm sure it's good enough for that. 10%, bit out, 5% or so. I'll show you the function to store data. So you see it's got like a DMM database, and you can select the position to store the information in, and then you can use the S key to store it with a short press, long press to enter and exit the database. There's a long press. When we go in, you see the previously stored values. Long press and out again. I'm now going to test continuity. It's quite quick, but can you hear it when you make continuity? It beeps, stops for a while, and then beeps, and then latches. That's quite annoying, but then my Uni-T does that as well. But bear in mind, it's not so surprising perhaps because they're using the same DMM chip. So just to show you, so it's my Uni-T 61D, and you'll hear the same thing happen. So I'm going to connect the probes together. You'll hear a short beep, a gap, and then it will latch. You see, it's the same. It's probably a characteristics of that common DM chip that's being used. That's a shame, but there you go. Now we're going to do resistance check. So on the left here I've got my LCR meter, my trusted LCR meter. So you can see I'm measuring the resistance now. It's 5K, and no issue there, I was spot on. Now I'm going to measure 1K. Okay, and then on the Gochifix. Perfect. This meter is actually very accurate. I'm quite impressed with it. So this is going to be 500 ohms. Perfect. Almost. Good enough. And finally 50 ohms. Good enough. In 1%. Now I'm going to check on the higher resistance, 10 mega ohms. Reading a little bit high compared with the LCR, but still within tolerance. Then I've got a 1 ohm, a precision 1 ohm resistor. Change the range. 1.11. Okay, well that's the last digit error. So now I'm going to check capacitance. So I've got 393 picofarads on my LCR, and then on the Gochifix 39. Excellent. That's very good. Okay. So I'm using an old variable capacitor from an old radio, which is quite handy for testing. I'm going to check the relative function now. So I'm going to 0 it. And then you can see I can increase the value of capacitance relative to where I press the relative button. And it can go negative as well. Look at that. With respect to where I took the relative reading. Excellent. Happy with that. Okay, now I have 50 nanofarad, 52 nanofarad. I'll have to switch relative off. Okay, yeah, 52 nanofarads, 53, 54. Okay. There's some electrolytics. Okay, this one's 100 microfarad. Okay, showing 91 on the LCR. And change the frequency, it should reduce that. Maybe 100 Hertz. Okay, 95. And then Gochifix. Make sure I get it the right way around. $199. Okay. Do note measuring capacitance is never as accurate on these type of meters as resistance is. Depends on the frequency they measure and the technique, whether they're attempting to charge and discharge using DC, or whether they're putting an AC signal through it and measuring the reactance. Just make sure it's discharged first. Okay, so this is showing 2.74 millifarads. Make sure it's discharged. .9. So this is a 2,700 microfarad capacitor. So it's kind of the accuracy you'd expect. The capacitors themselves are not particularly accurate, and then the method of measuring the least, a number of things to be desired as well, and different techniques employed by different meters. So now we're going to test a few semiconductors. So first of all, a couple of LEDs. So this one's got a forward voltage of 1.9 volts at 5 milliamps. Now bear in mind the Gochifix may use different currents, so we get a different voltage. 1.85, that's good enough. And you'll notice the LED lights when you're testing it, so that's good. Let's try a white LED. I expect the voltage should be higher, the forward voltage. Uh, 2.77 volts at 5 milliamps. .57. Notice that the Gochifix keeps current passing through the semiconductor on semiconductor test or diode test. That's unusual. And then a silicon diode, so 0.64 volts forward voltage drop. 0.57. Again, differences most likely because of different currents used to test the semiconductors with. Okay, I want to show the min and max horde, which I think is a really cool function. So I'm using it in resistance in this case, but you can use it on capacitance and sorry, not capacitance, you can use it on current and voltage as well. So you see I'm varying the potentiometer to vary the resistance, and it's capturing the highest and the lowest within this particular run session. I think that's really, really handy. One negative thing about this scope is I couldn't find any way to change the level. If you go into the voltage menu, you have volts per division up and down. But you see there's no way of changing the level. Otherwise, in other words, 0 volts is always in the middle. You can't reposition it to 0 volts is at, say, the bottom division or the bottom of the screen. You've got trigger, there's nothing in trigger. You've got mode. You've got level for the trigger, so you can move the trigger level using the F2 and F3 keys. But also, annoyingly, you can't hold either of those keys down and get the trigger level to move continually. You have to keep pressing F1 and F3, and that beep soon does your head in. But I do cover switching off the beep later in the video. So, very surprising. You'll note that there's a indicator on the left in the middle, like a pointer, which seems to indicate what that level's set to, i.e. 0 volts, always in the middle of the screen. I don't know whether there was an intention to put a function in to move the level, but it was forgotten about. Strange. That is a bit of a bugbear for me. I don't know why that wasn't included. So you can imagine that's quite restrictive because it restricts your range, especially if you're on DC voltage. You only get half the screen for your positive or negative swing. I'm going to show you how to save waveforms. So press S once to freeze it, long press it to bring up the save menu. So you've got save arrays or left and right to change position in memory. And then you long press again to exit. Long press to go into memory again, and then you can see you can cycle through left and right in the previously stored waveforms. Long press to get back to scope mode. That's pretty much it. I'm now going to test the oscilloscope function. To do that, I've got a BNC lead terminated at 50 ohm, and I'm using this adapter to connect it into the Gochifix. Right, it's 4mm input terminals. So that's the nice thing about having standard 19mm spaced input terminals. For inertia, do note. And so I'm going to put in a 4 volt peak to peak sine wave, and if we're going to test the bandwidth, it times up by 0.707, so it should be 2.8 volts, or as near as damn it. So we're going to increase the frequency until either it gets down to 2.8 volts peak to peak from the original 4 volts, or it falls apart. So here I am with a 10 kilohertz sine wave, 4 volts peak to peak. And 50 microseconds per division time base. So now I'm at 1 megahertz and no reduction in the peak to peak voltage. 1 microsecond time base. 2 megahertz. Still the input amplitude's good. I just change the range to make it a bit more visible. Four megahertz. 4 megahertz was still good. Now I'm down to the minimum time base at 200 nanoseconds, and we're at 6 megahertz input, and still we've got 4 volts peak to peak. So bandwidth looking good, but this is here is a restriction on this scope, right? Because you've only got 200 nanoseconds maximum per division, or minimum, whichever way you want to look at it, which really limits its use above 6 megahertz or so in terms of studying waveforms. So now it's to 10 megahertz, and we're only down to 3.8. So no problem with the analog bandwidth, but the signal is pretty overall at 12. Now remember that the sampling frequency we measured to be 25 megasamples per second, and the rule is that you can only acquire signals up to half the sampling frequency, so we should only be able to acquire signals up to 12.5 anyway. And look at that, 12.5 megahertz, and the wheels have come off, right? It's gone completely bonkers, which you would expect. That's why it's always good to do a teardown before you do a functional test. You can understand what's going on. Okay, cool. So bandwidth no problem, but practically the signals that or waveforms you can reasonably observe is up to 6 megahertz because of the limited time base. So now on to the real stress test, which is how well does it do with square waves. So we've got a 1 megahertz square wave, again 4 volts peak to peak, and up to 2 is looking a bit dodgy, and 3 the wheels have come off again. That's because of the limited bandwidth and sampling rate, which are effectively removing the higher frequency odd harmonics that you need in order to faithfully construct the square wave. If you refer to my functional review of the Finersi 2C23T scope meter, I spoke a bit around there about why you need bandwidth, which is significantly higher than the square wave fundamental, to resolve the square wave properly. You may want to pop in and have a look at that video for an explanation. Now here I've got the time base down to 1 second per division, and actually it goes all the way down to 10 seconds per division. And on the horizontal axis we've got 12 divisions, so that means we can cover a time period of 2 minutes on one trace, which is great for slow trending voltage signals, such as you might want to attach it across a power supply and then switch things in and out and see the impact of that load on the power supply. Or you might want to look at a capacitor discharging or charging, or how quickly the voltage drops after switching off a power supply to make sure it's safe, or whatever. But that's another useful feature, I think. And do note that the stats that they've got across the bottom of the screen only works up to 50 milliseconds per division. If I switch it up to 100 or anything higher, notice they disappear. So do note that. This multimeter does like to beep, especially if you put it in scope mode and you're using the keys to change the voltage per division or time base, and it can get a bit tiring, to be honest. It's quite a piercing beep, especially if you're changing the trigger level or something. So what I found was, even though it's not documented in the manual, if you just turn it on, you can see it says quiet mode off. But I found that if you hold down F4 and turn it on, but quiet mode on, so now it's blissfully quiet. But unfortunately it doesn't stay like that, so next time you turn it on, it's back. But what is documented is if you hold F1 and turn it on, it switches off auto power off mode, so it will work continuously without shutting down automatically. Now I thought, well, what happens if you do both F1 and F4? Unfortunately, it prioritizes F4 but leaves auto power mode on, auto power off mode on, so you can't have both, unfortunately. And one of the things I really like about this meter is how I can use the same probes for both the digital multimeter and the oscilloscope. So here I am measuring the DC supply voltage to a nano, and then let's say I want to look at, say, the pulse width modulation signal to an LED. I don't have to change my probes. I can use the same probes, just flick a switch, and then get my oscilloscope display without having to worry about having another probe. I just save it by pressing the S key, or freeze it I should say, and there we are. Now let's see what this scope is like for, say, diagnosing the signals in a AM radio. So what you can see here is what, 2 megahertz. So that would be the local oscillator frequency plus the receive frequency. What else have we got? And then we got 450, yeah, so 450 kilohertz. So this would be the IF frequency. Yeah, the signal's quite stable. It's well triggered. Just freeze it. Let's have a look. Yeah, so that's pretty good. I think, you know, clearly this type of scope is good for looking at lower frequency signals that you get in AM radios and audio circuits, etc. Pretty good for that. So this brings me to the end of the review of the Gochifix LG302. So let's have a look at the cons and the pros. So the first one's a bit subjective. There's no rechargeable battery. Personally, I'd like to have a rechargeable battery, but for some of those that maybe work out in the field and are looking for something that you can just pop into a shop and buy more batteries to keep you going, or to carry around spare ones, so that if the current ones go flat you can just pop into new ones and keep going. You know, I can see the advantages to that, but personally for me, I like a rechargeable battery. Then the next one, not having the ability to change the trace level, i.e. where the 0 volts level is when using the oscilloscope, is always mid-screen regardless of whether you're on AC or DC. That is surprising. I mean, after all, you can change the trigger level, which is a basic oscilloscope function, but why you can't change the trace level, which is another expected function, I have no idea. That's unusual and a bit restrictive. Another issue is the maximum sensitivity is only 500 millivolts per division, which means that it's not suitable for electronics really. It's more suited for diagnostics on such things as cars and boats and electrical systems rather than electronic systems, if I may say. But okay to see there's a signal there and to do basic fault finding, but nothing really serious in the field of electronics. And then also the minimum scope time base only goes down to 200 nanoseconds per division. So despite your 10 megahertz bandwidth and 25 mega samples per second sampling rate, it's not much use for trying to examine or analyze signals over 6 megahertz because they're just too small with 200 nanosecond per division time base. Another issue I have with this scope is the use of surface mount fuses which are soldered onto the board. And you might say, well, perhaps they're resettable. They're not. I tried purposely blowing both of the fuses and they were still open circuit after some time. So that is a shame because it's a real pain to unsolder them to replace them. And finally, don't expect 50 megasamples per second. If you solve the rest of my video, you would have seen that we measured the actual sampling frequency, and it was only 25 megasamples per second. So sampling rates overstated, which is not unusual for scopes or multimeters in this range or this price point. They're often overstated, but it doesn't really make a difference, because at the end of the day, with a 10 megahertz bandwidth and only a 200 nanosecond per division time base, you're not going to need the 50 megasamples anyway, so 25 megasamples is perfectly adequate. Now on to the pros. So first of all, as I said before, I love the fact that you can use the same probes for both the multimeter and the oscilloscope. I think that's really handy if you're out on the field. You don't want to be carrying around a oscilloscope probe with you. You just want to be able to find out if there's a signal there and use the same probes that you're using with the multimeter functions. Super convenient, and I love it, and actually that's why I wanted to review this meter. I also like the thought that both the oscilloscope and multimeter inputs are Cat2 protected. You'll note that some oscilloscope meters, whilst the multimeter inputs are Cat2 or Cat3 protected, the oscilloscope inputs generally are not. Some are, but the lower cost devices are not. So this scope benefits from that protection for both functions, both oscilloscope and multimeter, so that's good. I really like the accuracy of this meter. I thought it performed really well. It was not so great at millivolts and milliamps in the very low range, but that's because of the last digit error, which is to be expected. Other than that, I thought it was excellent at this price point. And also note that if you looked at the teardown section, it uses a multimeter IC, which is used on a lot more expensive and respected devices, such as those manufactured by Unity and others. So that's also a bonus point. I also like how the oscilloscope has up to 200 volts per division, which is great for poking around higher voltage AC installations. Obviously it's still not, you wouldn't use this multimeter for high energy applications, but you know, for poking around maybe mains voltages to see what the waveform looks like, switch mode power supplies and so on, I think that is very handy. I also like how the time base goes down to 10 seconds per division on the scope. That means on the screen of 12 divisions you can get up to 2 minutes of trace, which is great for slow moving signals. Something I was really surprised about this multimeter scope is how low the current consumption was. I don't know if you saw my video on the Finersi 2C23T, but the current consumption for that was over 400 milliamps, regardless of whether you're in scope mode or multimeter mode. Now, if you'll recall, when we looked at the current consumption earlier on in this video, the current consumption in oscilloscope mode was only around 105 milliamps. So that's like 25% of the current consumption of the Finersi. And then when you put it into multimeter mode, it's even better. It went down to just 55 milliamps. So if you were using 2,400 milliamp hour batteries, rechargeable batteries like I was, then you might be able to get up close to 20 hours of operation in oscilloscope mode, and to almost 40 hours in multimeter mode. I mean, I'd like to test that, but in theory it should be around that mark, maybe a bit less, but very impressive considering that you've got that microprocessor and that big LCD to drive. The other thing I really liked about this is the minimum and maximum peak recording and relative functions. I thought those are really handy to have on a meter. and were well implemented in the software, easy to use and straightforward. And finally, I know this is subjective, but some people may consider the use of standard AA batteries, which you can just pop into a shop and get some more when you're caught out on site, an advantage. So I'll leave you guys to debate that one. So in summary, I know this meter has some shortcomings, but overall I think it's still excellent value for money. And I think the great thing about this is where you can use the same probes for both the multimeter and oscilloscope, and I think that is just fantastic for applications where you might be using it to diagnose issues with cars, boats, motorbikes and that sort of thing. I think it's just excellent for that. Now, unless price is a real concern, I would not recommend this for somebody getting into electronics. You really need something which has a much more sensitive oscilloscope input. You're going to want a faster time base, and you're definitely going to want to be able to move the trace position so that 0 volts isn't always in the middle of the screen. So in summary, with a 10 megahertz oscilloscope and accurate multimeter and shared Cat2 rated inputs, I do think this still represents a good value for money. But if you're going to buy this, please do go in with your eyes open, be aware of its limitations. And if you are interested to buy it, in the description of this video you'll find a shop link, and I understand that will give you a significant discount on the original purchase price of around 25% or so. But do know I don't get any commission from it. It's purely for your advantage, and it's for a limited time only. So thank you very much for watching, and I hope you found it interesting or useful. And as always, please do give me a like, and I would really appreciate it if you would subscribe. It means a lot to me and does help my channel. So until next time, look after yourselves and take care.